Welcome back to Reconstructing Relativity, Chapter 5b, as we continue looking at radial motion. In Chapter 5a, we looked at four bugs, which are metaphorically representing the energy within a particle, as these four bugs travel radially out away from a center point and then back towards it to come back together in unison. In this chapter, we're going to expand that and add a whole bunch of more bugs flying in all sorts of directions in the plane, and we'll see what happens. We'll get a better picture, and we'll talk about this whole thing further. Now, before we get started, I want to just remind you again that we're using this bug metaphor to try to understand what's going on physically. But language can be tricky, so these phrases like what we see, apparently, what an observer measures, what actually happens. Just remember that vision, observation, measurement, these are all processes that have to be thought about, not just taken for granted. So we'll get into that later, much later down the road. Right now, let's try to imagine what could be happening physically. A particle we're representing as a pattern of motion of trapped energy. The energy always moving at speed c through its local space. A bug represents the energy moving within that particle. Let's add more bugs, let them go in all directions, not just in four directions. When the particle's not moving through space, here's what the motion looks like. Cyclic motion of energy, radially in and out. Now, what happens when this particle, or pattern of cyclic energy motion, moves through space? Let's run a couple of elaborate thought experiments. Let's imagine we have a stroboscopic camera so we can take some pictures of what's going on. First, imagine that we attach the camera to the car. As the car moves, the camera moves with it, always looking down at the antenna tip and the bugs around it. Suppose that we set the strobe so that it flashes 30 times for each energy cycle. Also imagine that in this strobe camera, every 6 flashes we change the color filter on the camera. This will help us keep track of the sequence of bug positions. And we're going to use the old chromatic Roy G. Biv sort of red, orange, green, light blue, and violet. So the first initial steps will be in red, and the final steps of the cycle will be in violet. Here's the picture we'd get if V over C was equal to 0.5. In other words, a particle moving half the speed of light, or the car moving half the speed of the bugs flying through space. This produces a gamma of 1.15, which is noticeable, but not a super strong relativistic effect. The motion of the pattern is towards the right in this picture. So this requires some more discussion and pointing out certain things that are visible in this diagram. Okay, so this is a really interesting graphic, and you might want to pause the video at some point and study this a little bit, but you can see a lot of things in here. First, the pattern is moving towards the right. That's the forward direction. So we can track the progress of the four bugs that we've already studied. If you look, the center dot always stays in the center because the camera's moving with the car. So as the ring of bugs spreads, starts out red because that's the first part of the time. So the bug's moving to the right, goes pretty slowly, and so it goes through red, it goes through yellow, goes through green as it goes to the right. That's the midpoint of the time. It goes past the midpoint of the time, gets to blue, then it turns around and comes more rapidly, much more rapidly back to the center point. On the other hand, if you look at the bugs traveling out to the rear, which is to the left in this picture, the initial movement is quite rapid, and it gets to the turnaround point in the yellow color, which is before the midpoint of the time. And then after that reflection, the trip back towards the antenna, still in yellow, then it goes through green, and then light green, and then light blue, and then finally the dark blue. Now if you look at the up and down bugs, those are lateral bugs in our model. So you see the spacing there, both out and in, is very even, and it gets to the turnaround point in the middle of the green time period, so right in the middle of the cycle. And everything comes back together at the end in purple. The rings get smaller and smaller as they zero in on the center point. Notice also that the boundary of this is an ellipse, and the ellipse, the ratio of height to width is gamma, 1.15, so it's a little taller than it is wide. So lots of things to look at here. We'll go on to the next slide. Obviously this was done on a computer program, and for the motion of all these bugs, the same sort of vector analysis was done to determine the relative motions. Since the triangles are usually not right triangles, some trigonometry was needed, and I used the law of sines to solve these triangles. Here's an example for a bug which is moving forward relative to the antenna, forward and rightward, and then returning forward and rightward with a higher velocity relative to the antenna. C, the velocity through space, is constant, always constant for every bug. Now here's the same picture for V over C equals 0.866 or gamma equals 2. Everything's the same as the other picture, just more so. Notice the ellipse is now twice as tall as it is wide, and the forward moving bugs go through red, yellow, green, blue, 28 steps to get to the front edge, and then just 2 steps to get back. Whereas the bugs moving rearward get to the back boundary in just 2 time steps, and then it takes 28 time steps more for them to get back to the center. Still, the lateral bugs going upwards and downwards in this picture still get to their boundary right at the midpoint, the middle of the green phase. So I started with the softer relativistic effects and went to the stronger one, just to show the contrast. Now let's take the different point of view. Let's mount that same camera on a stand and have the car drive underneath it. Now, instead of staying right over the antenna will be moving through our frame. I'm going to stay with the V over C equals 0.866 case, the gamma equals 2. And let's see what this looks like. Nice. Now we have the point of view of being still in space. In our car model, we're standing still on the ground as the car goes by. But in the physics view, we're still in space, not moving in space, and we watch a cycle of energy radiating radially outward and then returning back to the center point as the particle is moving. You can see the circles are clearly circular, both on the emergence and after reflection on the return, circular concentric return. Very interesting picture. Now let's animate this and show the moving elliptical reflection boundary. Again, we're looking at V over C equals 0.866, which gives us a gamma of 2. Note the 2-to-1 slowdown in cycle time when compared to a non-moving pattern of the same height. And again, the ellipse is twice as tall as it is wide. Again, that equals gamma. Here's an interesting graphic. It shows that the pattern falls apart if a circular boundary is used instead of an elliptical boundary. There's no harmonic return. Got to have that elliptical boundary for everything to come back together. Oh, and one more thing I noticed, the overall shape of this pattern also has a length to height ratio of gamma. Don't know if that has any particular significance, but gamma seems to be everywhere. So that wraps up this chapter for now. We will be coming back to make use of these results again later, though, for other purposes. In the next video, we'll be looking at yet one more mode of cyclical energy motion within a particle. Then, hopefully, with these three modes under our belt, we'll be fully convinced that any harmonic energy pattern would see the same effects, and we'll be able to move forward to discuss relativity further. Thanks for watching. My book's on Amazon. Like, subscribe, do all that YouTube stuff, and listen to this awesome clip from an awesome piece of music by Tom Stolby. See you next time.
Nations will rise and fall, and never see the world through these eyes. Dreams of falling, dreams of flying. A man who never dreams goes slowly mad. The dawn of science, the age of reason. This is the voyage of the mind's eye. This is the